All right. So thank you so much for the invitation. It's my great pleasure to have this opportunity to share some of my recent work on coping with heterogeneity and privacy in communication efficient federated optimization. So this talk is taking a slightly different perspective than some of the earlier talks in this workshop. We'll be looking at some of the algorithm design from an optimization perspective, trying to understand how to address heterogeneity and privacy issues in a sort of approval manner from the optimization side. So this talk is based on joint work with Zhize Li, who is currently a research scientist in my lab, and Boyue, a graduate student in my group, as well as Hao Yuzhao, who is a PhD student at Princeton Computer Science in Sanjeev Arora's group, and Peter from COST. All right, so generally speaking, it's a type of optimization problem we're interested in machine learning and a lot of other fields is this kind of empirical risk minimization problem, where we're given a data set and the goal is to optimize or minimize the loss function that can be seen as an average of the sample loss, where the small L function is essentially a sample loss. And the total number of sample we have is denoted by the capital letter N. So if you're working in the classical machine learning field, where you are designing simple models like least squares, logistic regressions, this loss function will typically be a convex function, or sometimes strongly convex functions if you add regularizers. But in the modern days, increasingly the problem we are dealing with are non-convex in nature. This runs through simple problems such as PCA, principal component analysis, where our goal is to fit some simple hyperplanes over our data sets, or more generally training any sort of neural networks. And in today's talk, we'll be primarily focusing on non-convex optimization problems. All right, now, instead of solving the problem in a central way, in the context of federated learning or distributed learning, we're primarily interested in solving this problem in a distributed fashion, either due to privacy or scalability reasons, where the data is instead distributed over multiple locations, or workers, or agents, or clients, depending on which field you come from, you may call them differently. For simplicity, you can imagine instead of having the whole data set at a central location, we'll actually split the data either actively or passively. For example, in federated learning, we actually cannot control how we split the data. But roughly speaking, let's say we have a data splitting mechanism, and the data will be actually distributed at different clients, and each client holds its own local loss function, say Fi, which now is computed over its own sample local data sets. Right, so we'll be using small letter n as to denote the total number of agents or clients in the problem. And for simplicity, if we assume the data evenly split, then M, which is capital N divided by small n, becomes the number of local samples that each agent holds. Right, so it has been already mentioned multiple times by different speakers in this workshop. There are a lot of unique challenges when we're dealing with optimization problem coming from this sort of federated or decentralized setting that sort of go beyond the classical or traditional paradigm of decentralized optimization, which by itself has been really a central topic in optimization that has been studied maybe more than 20 years. But in this sort of federated learning or machine learning world, the sort of new challenges we're dealing with includes, for example, communication efficiency, as increasingly we're training these machine learning models on mobile devices or band-limited sensors. So communication with a parameter server also its neighbors become difficult when the bandwidth is limited. And there may be stragglers in the system that really cause long delays in training. So communication efficiency becomes sort of a prime objective when we try to design algorithm that has optimized performances. In addition, the performance of the algorithm in terms of convergence can become very slow, or sometimes even result in non-convergence issues when the local data sets are highly heterogeneous. which essentially, again, many speakers have mentioned this. The data sets we have across different agents can, instead of having IID distributions, they can be highly heterogeneous and non-IID, and causing significant performance degeneration. A last bit of the consider that the data is the privacy issues. Distributed optimized learning or federated learning on first glance may seem to be quite innocent with respect to privacy, because we never ask the agents or the clients to directly share the data, but maybe only some sort of model updates. However, this does not necessarily mean the algorithm is actually secure. Indeed, there has been a lot of recent work that show security issues or privacy leakage of naive federated learning algorithms. So we had to actually design privacy preserving algorithms that can actually guarantee the user privacy in sort of a provable manner. So with these considerations, let's first look at communication efficiency. Now, the simple way to think about the communication cost of the algorithm is basically the product of two numbers. One is sort of the number of communication runs we need to run in order to train the algorithm. The second is sort of the communication cost per round. And there has been a lot of different algorithms try to optimize either one of this term or both of the terms at the same time. So in order to sort of optimize the communication runs to train the algorithm, people often take this so-called local method approach. Instead of just run one step of SGD as a local agent or client, we actually perform multiple runs of computation in order to reduce the total number of communication runs. So this is essentially the scheme used in the well-known algorithm federated averaging or other methods, local SGD and so on, that this is we are sort of training of more local computation in order to achieve better communication efficiency to reduce the number of total communication runs we need to run. Alternatively, in order to reduce the communication cost per round, we could also do communication compression in the way that instead of just share the raw high resolution message or the model or the gradients, we can actually compress these messages first, either through doing specification. For example, instead of transmit all the entries in a high dimensional vector, I could only transmit a small number of the entries. Or I could do quantization, instead of sending 22 bits per entry, I could be only sending 1 or 2 bits per entry, right? So this way essentially allows me to reduce the communication cost per round and also improve the overall communication efficiency. So in this talk, we'll be primarily focusing on communication compression to improve the communication efficiency. And we'll be thinking about communication compression in fairly generic manners. So any sort of popular specification or quantization schemes can be embedded and used in the algorithms we are going to talk about. All right, just to set up the stage, commonly, we will be thinking about two types of distributed schemes. One is sort of classical server-client model, where there will be a parameter server that helps to coordinate the information sharing between the agents. And this is very popular, again, in the literature. On the other end, we will also talk about this network or decentralized model, where there is actually there will not be any sort of parameter server, but rather the clients will be sharing local information over some predetermined network topology. It's fairly easy to go beyond the fixed topology and talk about time varying topology. But for today's presentation, again, we can just naively think the topology is fixed, but every clients can only be sharing information with the neighbors instead of sort of broadcasting over the entire network. And sometimes this sort of decentralized model can be more communication efficient, especially for distributed training, because we sort of avoid some sort of the communication jam with a parameter server when everyone tries to communicate to the same node that is a parameter server, and sort of help us to reduce the delay in the system. We'll be talking about two algorithms in today's talk. The first one will be actually looking at the network or decentralized model, where we'll be focusing on how to design algorithms to cope with data heterogeneity. And towards the end, I'll spend a couple of time, maybe around 5 to 10 minutes, to talk about a new sort of unified framework we developed for private federated learning in the server client model to cope with the privacy issues. All right, so let me just start with a prelude before I jump into the algorithm I want to talk about. Since we're going to use compression as a primary scheme to do communication compression, naturally, I want to look at what should we compress, right? So if you look at this sort of naive parameter server model, usually all the agents will be sending its local gradient evaluated at some global parameter xt to the parameter server. This is sort of the standard thing that the algorithm will sort of proceed in the classical setting. Now, if we want to compress this algorithm by only using compressed information, the first idea that will come to mind will be just compress these messages directly, right? So instead of sending the local gradient, I will be sending some compressed version of this local gradient, and then the parameter server will just do an average of this compressed gradients and perform an update. So this type of scheme will be called sort of direct compression schemes. And surprisingly, it turns out this kind of direct compression actually doesn't really work very well, even with some very simple compression mechanisms. And to show why this is the case, I'm going to borrow this counterexample constructed by Zhize. And this is a really very simple model where you can imagine you only have 3 data points in a sort of ridge regression problem, where there are 3 agents. Every agent has just say 1 data point. So each of them just have 1 feature vector, A1, A2, A3, and so on. So if you look at the global problem, this is the most benign case. This is a strongly convex problem. So we should expect we can solve this problem very easily. Nonetheless, if you run this compression algorithm, this direct compression algorithm from some naive, say, initialization, which say is sort of this all-one vector multiplied by a number b, and let's say we use a compressor to be the so-called top 1 compressor, meaning it will only retain 1 entry in your message that has the largest magnitude. So if you do so, with some very simple calculation, you see essentially every compressed message essentially only retain 1 entry in the message. And when you add them together as a parameter server, the next iterate actually becomes a scaled version of your initialization. And that scaling actually blows up, is a strictly positive, is a number strictly greater than 1. So that basically means this algorithm actually diverges exponentially. Even for such a very simple toy example, direct compression actually leads to a divergence in the optimization problem. So the question is, if direct compression doesn't really work, how should we, what should we compress, and how should we design the algorithm? A better scheme proposed in the literature is this so-called shift compression approach. And in this approach, instead of using a direct compression of local gradient, we'll actually try to sort of design some sort of surrogate of the local gradient, say these GITs. And these GITs are constructed by compressed messages that will be sort of stored as a parameter servers. And we're going to update this compressed surrogate of the local gradient using this kind of difference compression scheme. So instead of do direct compression, now we are going to do this kind of difference compression, where these GITs will be updated recursively, where the next GIT is updated by the previous GIT, plus a compression of the difference of the current local gradient and the previous GITs. So again, this GITs is not direct compression messages. but it can be constructed using compressed messages alone. So the parameter server doesn't need to do it, doesn't need to know anything beyond the compressed messages in order to construct such surrogate information. And this kind of shift compression turns out to work remarkably well and help to accelerate the convergence in many of the compressed optimization algorithms. So this type of shift compression schemes essentially is what we are going to use when designing our federated learning algorithm with communication compression. All right, so now with this sort of basic setup in terms of what kind of compression scheme we are going to use, now let's get into some of the algorithm designs for different settings. So the first algorithm we are going to look at is try to design fast convergent algorithms for decentralized non-convex optimization when the local data can be potentially heterogeneous. And this is joint work with, again, Yuejie, Yuejie, and Peter. So before we introduce our algorithm, let's look at what kind of results that has already been achieved by prior art. So two of the state-of-the-art algorithms, CHOCO-SGD and Deep Squeeze, essentially achieve a convergence rate that is on the order of this, say, order of G divided by epsilon 2 to the third order, where epsilon is the accuracy level you want to achieve for optimizing over this kind of decentralized network. On the other end, if you look at the convergence rate we can achieve using an algorithm without any compression schemes, the convergence rate actually only depends on the accuracy level on the order 1 over epsilon. So if you benchmark the prior rates achieved by CHOCO-SGD or Deep Squeeze with the rate achieved by uncompressed algorithms, we immediately see there are 2 points that can be potentially improved, right? So the first one is the slow convergence rate achieved by prior algorithms, where essentially their rate is not optimal compared to the uncompressed version. So that means if you run these previous algorithms, you may need more communication run in order to converge. But perhaps the most stringent issue is the incompatibility with data heterogeneity in the convergence of previous algorithms. So I haven't told you what this parameter G is. This parameter G actually helps us to measure the data heterogeneity across different agents. In the literature, this is either measured by looking at the gradient of your loss functions. You will require the loss functions or the sample loss to be bound to have bounded gradient, and that is effectively sort of limits the level of heterogeneity of the data set. Or you're going to look at sort of this so-called dissimilarity measures that look at the difference between the local gradient with the global gradient. Either way, the previous convergence rate actually scales linearly with this heterogeneity parameter G. So if you have a data set that can potentially have unbounded heterogeneity, this G can be unbounded, and you actually lose convergence guarantees for these previous algorithms. So a natural question is, can we actually converge at the rate on the order 1 over epsilon, where we can actually eliminate the dependency with the heterogeneity parameter in the convergence rate. So we can ensure the algorithm can converge at a faster rate under arbitrary heterogeneity. The answer turns out to be yes, otherwise I will not be giving this talk. And the way to do this is essentially by introducing this idea called gradient tracking, that is sort of a very stable algorithmic idea in decentralized optimization to the design of this kind of compression algorithms. So let me just tell you maybe through 2 slides what this gradient tracking is. Let's, instead of directly jumping into our algorithm, let's look at a very simple algorithm, which is just try to decentralize gradient descent into this sort of decentralized network topology. On the slide, we are showing just the standard update rule for centralized gradient descent that really requires no explanation, that everyone knows what this is. When you try to decentralize this over a network, you can no longer have a centralized consensus copy of the parameter Rather, every agent or client will have its own local copy. And when it tries to update its own local estimate, it will essentially consult with its neighbors and sort of getting a mixing, will mix sort of together the local, its neighboring estimates to replace the central estimate. And instead of sort of update the parameter along the direction of the global gradient, now we are going to update along the direction of the local gradient. So this is sort of a naive extension of this centralized algorithm to the decentralized setting. Well, we know the centralized gradient descent works very well when we use just a constant step size, especially for strongly convex problems, we can actually achieve linear rate of convergence. But on the other end, for this naive decentralized algorithm, well, if we insist on using constant step size, the algorithm actually does not converge to the optimal solution. And this is actually fairly easy to see in the sense, just imagine if all the agents now actually sit at the optimal point x star, so the gradient of the local loss function is actually 0. However, the gradient of the local loss as the optimal point x star is actually non-zero. So if you execute this DGD rule, the local gradient is actually not 0. So it will actually drag the iterates away from the optimal point. So in other words, this sort of naive decentralized GD algorithm does not converge primarily because we really shouldn't be updating our parameters along the direction of the local gradient, but rather the global gradient. But how can we fix this? How can we get some information about the global gradient without actually accessing the global gradient? And this comes this idea of gradient tracking. And as the center of this gradient tracking idea is really using this control theoretic tool called dynamic average consensus to maintain and track an estimate of the global gradient at each agent. So for example, if you look at the way we're updating the local parameter, instead of now update along the direction of the local gradient, now we are updating along the direction of some estimate of the global gradient, SIT. And this SIT is essentially constructed using this dynamic average consensus tool, where instead besides doing this mixing about the information from the neighbors, will also include the so-called gradient tracking term that look at the difference of the local gradient at 2 consecutive parameter updates. I will not have time to get into the detail about why this is a good approach, but this kind of idea essentially has been very powerful in the literature of decentralized optimization and help to fix a lot of the non-convergence issue when we try to decentralize many of the nice algorithms in the centralized setting to the network domain, including some of the second order methods as well. And there is a long line of literature that look at these ideas. Many times it has been rediscovered or discovered under different guises. I will not be able to get into the details of this, but we'll be actually also using this gradient tracking idea in the designing our algorithm. So now with the introduction of this gradient tracking idea, and also the shift compression we mentioned before, we can formally introduce this Beer algorithm. And to make the notation concise and simple, we are going to use matrix notations that sort of collect all the local model Xi's as columns of this matrix. So this matrix X basically collects all the local models across different clients. And we are going to use the notation gradient capital Fx, where each column contains essentially local gradients evaluated at local models. And our algorithm essentially will contain 2 parts. The first part is sort of the model update part that will be essentially executed in parallel at different agents. And the way the local models will be updated, again, will include 2 components. One component is this information mixing across the neighbors. However, instead of mixing directly those local model XTs, we'll be actually only mixing these HTs, which are actually those compressed surrogate of the local models that we talked about earlier when we introduced the shift compression scheme. This is because, again, we never share the model directly because of compression. So we only can maintain some sort of compressed surrogate of the local models at every agent. And we'll also be updating the models along some search direction VT, where these VTs are essentially the estimate of the global gradient estimates across the agents. And as you can imagine, we'll be updating these gradients using the gradient tracking trick. And this will also contain essentially two components. One component is this mixing component, where instead of, again, mixing the global gradient as the agents, we actually, again, only being able to mix the compressed surrogate of these local gradients due to compression. And beyond this, we also need to include this very important gradient tracking term that helps us to really address the data heterogeneity issues. The last component will be basically how we actually update and track these compressed surrogates. And this is essentially done by using the shift compression scheme we mentioned earlier. So altogether, this BEER algorithm essentially embeds ideas of shift compression and also gradient tracking in order to solve this kind of decentralized non-convex optimization problem. All right, so with this algorithm now in place, we can now talk a little bit about its convergence rate. And in order to find some sort of epsilon accuracy results in terms of finding first order stationary points of this non-convex problem, the number of communication rounds BEER requires essentially scales on the order 1 over rho to the third order times alpha times epsilon, without any sort of bounded gradient or bounded similarity assumptions. So essentially, the convergence of BEER doesn't require any kind of data, can basically carry out with arbitrary data heterogeneity. This parameter G that you saw in the previous algorithm essentially does not occur anymore. The two other parameters that enter into the convergence rate, one is this alpha, which is essentially the compression ratio. If you're using a compression scheme that is, say, a random specification scheme, if you only communicate k entries out of the d entries in a high-dimensional vector, then the compression ratio is essentially k over d. So the higher amount of compression you have, the more iteration you need. And this beta parameter is this so-called spectral gap of the network, which essentially looks at the connectivity of the network. So basically, the closer beta is to 0, the poorly connected the network is, and again, more number of iteration rounds you need in order to converge to a quality solution. Now, if we assume both rho and alpha are constants, then essentially we can claim the convergence rate of this BEER algorithm is essentially on the order 1 over epsilon, which matches with the convergence rate of the uncompressed algorithm and doesn't require any sort of bounded gradient or dissimilarity assumptions. So altogether, we answer the question that we now have designed an algorithm that can converge at sort of the near optimal rate 1 over epsilon under arbitrary data heterogeneity. And this greatly improves the best convergence result of the prior art, CHOCO-SGD and deep squeeze, in terms of both the dependency with the accuracy level and as well as the dependency with data homogeneity assumptions. Before I conclude the discussion on BEER, let me just show one toy example that demonstrates that this gain we have in the theoretical convergence rate is not just a theoretical improvement, but actually corroborated by numerical simulations as well. So this is sort of a toy example we've done on training a very simple neural network structure on so-called using an unshuffled MNIST data set. What I mean by an unshuffled data set is imagine you have a number of clients the first client may only see the digit 1, the second client may only see the digit 2, and so on and so forth. So this creates a scenario to mimic data heterogeneity using this sort of MNIST data set. And both Beer and CHOCO-SGD are using the same kind of communication compression scheme. And we can see in this toy example, indeed, CHOCO-SGD doesn't really work well when the data are highly heterogeneous. Although CHOCO-SGD works really quite well when the data are heterogeneous, when we actually shuffle the data set to create a sort of IID scenario. But when the data is actually non-IID, we see that the performance of CHOCO-SGD degenerates significantly and leads to poor testing accuracy as well. On the other end, our algorithm Beer converges still fairly well, even in this highly heterogeneous setting, using communication compression, and achieves much better performance than CHOCO-SGD on test data as well. So altogether, we see in this sort of decentralized optimization framework, we can actually seamlessly combine the idea of gradient tracking with shift compression to design algorithms that can converge at the optimal rate under arbitrary data heterogeneity. All right, so with that, that covers the discussion on the Beer algorithm. Now I want to use the rest of the time I have to talk about a new framework we designed for private federated learning when we have communication compression in the server client model. This is joint work with Zhize, Haoyu, and Boyue. So we've seen a lot that in federated learning, there's a lot of multitude of considerations that we want to achieve or meet when designing algorithms. One is this privacy problem, where we not only want to preserve the privacy of the entire data set, but actually we want to do one step further, that we can actually say we preserve the privacy of the local data set to prevent even data leakage across different agents or different clients. We also see there are multiple ways we can do communication with the parameter server by using communication compression. Within even the shift compression, we could have very different schemes of the compression compressor designs by using either specification or quantization, or potentially new designs of compression schemes. In terms of the local computation, when we run some kind of stochastic local gradient updates, there are also many choices we can take for the local clients. We could be using SGD, we could be using full batch GD, or we could be using some of the variance reduction algorithm like SVRG or Saga algorithms. So there are many different design choices when it comes to both the computation and the communication aspect of the algorithm framework. Can we actually design kind of a unified framework that allows us to capture all the three aspects of the considerations when we have communication compression? And more importantly, we want to be able to characterize the trade-off between these different considerations. And maybe there is a complete characterization across the trade-off of privacy, utility. Utility here means, say, the convergence or the final accuracy of the model, and the communication cost. We want to have a trade-off of all these three aspects in sort of a unified manner. And because of this motivation to design a unified framework, we introduced this algorithm framework called SoteriaFL, and it was fairly interesting. I also heard Yiran mention their Soteria algorithm for secure federated learning. So obviously, we share the similar passion or interest with Greek goddess Soteria, who is happen to be the goddess of Greek the safety in the Greek literature. So the highlight of our SoteriaFL framework is that we generally allow very flexible local gradient estimators. So we can incorporate many different choices of existing local stochastic gradient estimators, but can also potentially incorporate new ones that will be developed in the future literature. We are protecting local data privacy through the use of the notion local differential privacy, which is a stronger notion of privacy than just guaranteeing the data privacy of the entire global data set. And I believe we are also the first one to look at this kind of privacy guarantee algorithmic framework when using the state-of-the-art shift compression scheme that I also introduced in the beginning of the talk. And finally, our framework comes with a comprehensive characterization of the trade-off between privacy, utility, and communication. Specifically, at the client level, every client essentially does sort of the following, where it will first try to construct a local gradient estimate, and instead of directly compress this local gradient estimate, you will first try to add in some compression mechanism, some privacy mechanism set by using, for example, the Gaussian mechanism to guarantee local differential privacy. And our algorithm actually tells you what sort of the variance you should be used in the mechanism in order to guarantee a certain level of differential privacy. And then we'll be basically running this shift compression scheme to compress this noise injected gradient estimate. And at the server end, the server will essentially aggregate all the compressed information it collects from the client, perform model update, as well as do an update of the global shift that it is accumulating over time. So essentially, the SoteriaFL framework is a quite natural framework for injecting privacy guarantees to compressed federated learning algorithms. Now, without getting into the detail of the sort of convergence trade-offs, different trade-offs we can guarantee for SoteriaFL, I'm going to just highlight one aspect of this trade-off. So in the paper, we actually talk about many different, we have a general framework, and then we instantiate our general framework to many different choices of local gradient estimators and give concrete performance trade-offs. Now here, I'm just showing one scenario that is sort of also the kind of typical scenario. And the quantity I would like to highlight is how this trade-off actually play a role, sort of pans out when you have compressions in your algorithm design. So imagine we want to guarantee local differential privacy. And in particularly, let's say we want to guarantee epsilon delta local differential privacy. And you could be using different compression operators based on how much compression you want to do for the message you are communicating with the parameter server. And let's say the compression ratio is denoted by the parameter alpha. So as you increase the compression ratio, your communication complexity will be dropping over time. And in particularly, is scaling with the compression ratio is on the order 1 over square root of alpha to the third order. So you actually gain cubically with respect to the square root or 1 over square root of the compression ratio in terms of communication. But on the other end, as you compress more, the accuracy will actually drop. Fortunately, it turns out the accuracy only dropped at the order of square root of alpha. So if you compare the gain you are getting from doing compression versus the drop in terms of accuracy, it seems we are actually doing pretty good in the sense we are saving a tons of communication. We are only dropping marginally or sort of by a small factor in terms of the accuracy when we have compression into play. In the paper, we actually characterize the trade-off in a much more accurate manner with dependencies with all the parameters. And on the slide, I don't want to crowd you or sort of bore you with all the details, but I want to just highlight this dependency with the compression ratio and highlighting how this actually enters into this other trade-off pictures at different orders. All right, so to summarize in the talk, I essentially covered two algorithms. One is this beer algorithm that is designed in the decentralized setting. And we show by using gradient tracking, we can actually meet the convergence rate of uncompressed algorithms even under arbitrary data heterogeneity. On the other end, we also talk about this unified private federated learning framework, SoteriaFL, we designed and highlighted the trade-off between accuracy and communication when you have different compression ratios for the algorithm. And in the future, we want to continue working along this line work. Particularly, we also want to look at privacy preserving algorithm in the decentralized setting under data heterogeneity, and potentially even combine with local methods such as federated averaging to further improve the communication efficiency of these algorithms. If you're interested, you can find the papers on my website. The SoteriaFL algorithm is actually just uploaded on archive, and I believe it will be announced tonight. And I want to thank all the funding agencies to make this line work research possible. And with that, I want to conclude. Happy to answer any question you have.
Okay, all right. Thank you so much, Dr. Chi, for the great presentation. Okay, so is there any questions in the audience? Okay, can you please come here? All right, thank you. Yeah. You can come here.
Hi, Yuejie, nice talk. So this is Tian Bao. I just have a question about the first work bill. So you mentioned this complex one epsilon is for the communication complexity, right? How about the iteration complexity? Does the algorithm have the local updates?
Oh, our algorithm actually does not have local updates.
So
it only does compression. So basically, the model update is just done in one shot.
So the communication complexity is just iteration complexity, the same thing.
Yes, that's the same thing here. Yeah, it will be interesting actually to also combine local updates in the algorithm. And we do have some ideas for doing that. But in this beer algorithm, in fact, in all the algorithm I talk about into this talk, we are not doing local updates. We are only doing communication compression.
Okay, so but another question is, since you focus on non-convex problems, right? So for general non-convex problem, we know that the lower bound for finding the epsilon level station point is 1 over epsilon 4, depending on how you define this convergence measure. So, but you have the complex 1 epsilon. What is that? I mean, is there any contradiction there? I mean, the lower bound is 1 epsilon 2, right, according to this.
Oh, these are communication wrongs, right? These are not the IFO complexity, the incremental first order.
Okay, yeah. So a related question is, you said this communication complexity does not depend on the heterogeneity constant. Does the iteration complexity depend on that?
I don't think it depends on it, but I think that you get slightly different bounds. There will be an extra term in the results. I can pull out the detail. I can share the detail with you offline. So the communication wrong here is assuming you do basically full batch full gradient computation.
Okay. Thank you. So my last
so this is sort of simplified result.
Yeah. So my last question is, can you talk about the intuition of this algorithm? How you get rid of this, the dependence on the G?
Yeah. So that's a very good question, and it's a little bit hard to get into the detail without showing you the proof. In the paper, we did give you some sketch, the key idea. But one thing basically I can tell is, it's really the key is doing this gradient tracking trick. The previous algorithm, the CHOCO-SGD, does not have this gradient tracking component. And by doing this gradient tracking, that really helps you to kind of mitigate the heterogeneity issue. In some sense, you can imagine that's kind of saw intuitively from the toy example for DGD, right? Instead of searching along the local gradient, you actually now have a better view of sorry. You have a better view of what the local gradient, you have better view of what the global gradient is, and this helps you to get the heterogeneity issue. Sorry.
Okay, all right, thank you. Yes. Do you have any other questions? Let me check if we have any questions in the chat. Okay. Okay, great. Dr. Zhi, thank you again for your time and the great presentation of your work. So is this, you mentioned the papers will be available on archive, right? Is also the code will be released?
We plan to do that, but it's currently not. We're still doing some more experiments.
Okay, that's fine. Just wanna,
the code for beer, I think, is released,
Okay.
but the private one is still kind of in the pipeline.
Yeah, that's totally understandable. Yeah. All right. Thank you so much.
Thank you very much.
All right. Thank you.